So we are now in 1974, and you left Israel, you went back to the US, and you spent a little period in Berkeley, again, teaching a little bit, if I remember correctly.
Correct. I actually did not plan to leave Israel at all. We were I was asked by Paul Witherspoon to take over his courses at Berkeley for 1 year.
Which course was it at?
His course was Flow Through Porous Media, but while I got there, I was also asked to teach an introductory course in geology to undergraduates, which was kind of a challenge for me because I was quite out of geology by then, and I, of course, never taught geology. This course was taught by Professor Dick Goodman, a rather well-known geological engineer, expert in rock mechanics, who focused on landslides and various things like that, but he had extremely disorganized notes, if any. So it was quite a challenge, but it was fun.
Did you rebuild all the notes of the code?
I actually took his notes and built my own course around his notes. And I didn't want to put a huge amount of time into it because I knew I would only teach it one time. So the idea was to go for 1 year, but then while I was in Berkeley, I was asked to come and visit Tucson. I had a joint project with Sid Yakovitz here, and Gene Simpson, who was the acting head of the department here at the University of Arizona, as well as Lucien Duckstein, a professor, thought it would be a good idea for me to come because they had an opening. The Chester Kiesil, who was a professor in the department, unfortunately died on the court ball, actually, on the ball court. And so they had this opening, and they thought about me as coming here. And that's how it developed, that I actually stayed here, because there was no intent of staying at that point.
And from the scientific standpoint, you started your love with geostatistics while you were in Israel, and then you carried it on here in Tucson, basically.
Well, as I said, actually my interest in geostatistics started with the contact with the geostatistics group at the School of Mines. Then while I was in Israel, we spent a summer in France, and I got more heavily involved in geostatistics. I also started doing inverse work, which I don't think we had time to discuss before, but that was another project that I worked on while I was in Israel, started actually working on the inverse methods. And then when I came to Tucson, Guylain de Marcilly came and spent a year with me here. I spent another summer in France, and this way I got more and more involved with geostatistics.
Which you brought to a high level when you came to Tucson.
This is really where I really started doing serious work on geostatistics here in Tucson.
So let us talk a little bit about that. And,
Okay. The first thing, I might have mentioned some of that earlier, I don't know, but the first thing that I did was kind of combine inverse methods with geostatistics. Two of my very first students, one a PhD student, Abdallah bin Sariti, and another student from Australia, Peter Clifton, have worked with me on this question of how do you build geostatistics into groundwater flow models and combine it with inverse methods to get a better estimate of parameters and therefore come up with better predictions of groundwater flow. So you could almost see this as an early convergence of inverse methods, which originally were applied in a completely deterministic context, geostatistics, which is really a statistical way of describing spatial heterogeneity, and what is now known as stochastic methods, where you build all of these, combine it with predictive models, and built into them levels of uncertainty. The building of uncertainty, by the way, evolved because I had no background in statistics when I came to Arizona, except, my geostatistics was the extent to which I knew statistics. So with time, things developed. And in fact, you coming here and working with me on inverse methods, statistical inverse methods.
Me working with you, not you working with me.
Well, the two of us working together, and Sid Yakovitz. My work with Sid Yakovitz and with you, I think, is what brought statistics in a formal way, I should say, and therefore in a more rigorous way, into what we started doing on a more ad hoc basis earlier. So this was like I would say by the mid-1980s, when you completed your PhD, Jesus, I think we had this statistically based inverse methodology where you take into account possibly prior information, measurements of permeability from pumping tests or whatever. You build it directly into your inverse method, something that was not originally done, something that I started thinking about in Israel, but really all of this came into kind of a full fruition in the mid-1980s with your dissertation and with Javier Sampers. And from then on, we started working more toward what is now formally recognized as stochastic hydrology. But I would put the mid-1980s as the time when this started, with one exception. And that is Larry Winter, who did his PhD with me and finished it, in fact, in the early 1980s. But he ended up doing stochastic work on dispersion, but he really started from a completely deterministic point of view, where his original task was to try to understand Jacob Beers and his former student, Yehuda Bachmat. They together developed a deterministic theory of dispersion, explaining, what makes up the dispersion tensor. And that work, which is partly described in Jacob Beer's famous book on flow through porous media, people, and certainly we, found very, very difficult to fully appreciate. So I hired Larry on a project related to Nuclear Regulatory Commission, ultimately related to nuclear waste disposal issues, to try to understand Jacob theory. And out of this then grew his stochastic, I would say actually the very first one, stochastic theory. I should say it was done without knowledge at the same time that Lynn Gelhar and Axnes published a very, very similar work of their own, completely independently. Larry worked for his PhD dissertation on a stochastic interpretation of dispersion. And Larry's, I think, came out 1 year it was published 1 year after the Gelhar-Axnes paper, but they were done literally just about at the same time. His PhD dissertation appeared on the same.
Let me go back a little bit to the inverse problem and geostatistics, and because at the time there were many people working on the problem. I mean, the need to calibrate models
on inverse
was
methods
being felt.
Mm-hmm. Yes,
by many, and it was you, or it was Cooley, especially Cooley, Dick Cooley.
Yes.
It was Peter Kitanidis also
Billy
working on that. Billy.
There were many people. There were chemical engineers working on this. There was a group at the University of Southern California with John Seinfeld, who is now a professor at Caltech, whose work I admired at the time. In fact, I was with some communication with him. There was a Bayesian methodology published also in the petroleum industry by Gavalas and others. So there was a lot of activity there. But, we took an approach essentially which was multi-objective. This concept that was started, as far as I'm concerned, with not just Amsalem and Demarcelli. There was, I think, a paper by King, published a little bit earlier. There was a professor at Berkeley, actually, also I think in structural engineering, who also has done something like this, where instead of just trying to minimize, say, the sum of square differences between predicted heads and observed heads, you build in a penalty function for coming up with parameter estimates that in some sense are not reasonable. So the idea of Amsalem and Demarcelli was come up with a parameter space that is relatively smooth. I think I might have been the first one to introduce this idea of bringing a penalty function in which you penalize the parameter, or penalize the I don't know what you penalize the process by, in other words, you want your parameters to be as close as possible to measured values, say that you obtain by pumping test or slug test or something like that. But it doesn't matter what the penalty is. This idea of penalizing or regularizing your space originally an idea attributed in mathematics to Tikhonov, came to be actually used in various ways, I would say, in the early 1970s by various people, including ourselves.
You did a lot of work on inverse modeling based on inverse modeling of groundwater flow.
Yes.
But you didn't do the equivalent work or as much work as was done with flow by taking into account or by considering also inversion jointly with transport. Is there a reason about that?
Well, first of all, I was not working really on transport. I was not doing transport modeling at the time. Don't forget, at that time, there wasn't much information about transport. After all, the need to develop transport models came primarily from the need to interpret tracer tests. And so there weren't so many large-scale field tracer tests published. There was some laboratory stuff being done, but most of it being interpreted analytically based on analytical solutions. The real interest in transport started with the discovery of major pollution issues in the 1970s, 1980s. So that's where the big work started on transport. Most groundwater hydrologists, I think, until the early 1970s, did primarily flow. So the focus was on flow. Plus, there were so many problems encountered in solving the inverse problem with flow that to start thinking about doing it jointly with transport, I think, was premature.
No, plus there were plenty of problems to solve. You say it very casually, this thing of penalizing departures of parameters from their measurements, but the idea actually is much more subtle, the way I see it. You're penalizing departures of parameters at a point where you have not measured. And this is the great thing of the geostatistical formulation.
But you can do it geostatistically.
That's correct.
But what I actually started doing in 1973, my first paper there, was you penalize at the point of measurement. So you parameterize, you fit some functional form, and the one that I fitted was very simple. Essentially, you divide the aquifer into zones, and you ascribe a single value of permeability or transmissivity to each zone. And then you say, well, in this zone, I have some pumping tests, and I have, say, an average value of transmissivity there, where I want the model to give me back a transmissivity which is not too far from my pumping test value. And you do it zone by zone. Later on, the geostatistical aspect actually was built into it later. The original thing was just this zonation.
No, but it was also, I mean, you did it when you came to Tucson with Vinsariti and Peter Clifton
then, yes.
and myself.
Then yes. Then yes.
So that's, so there were several breakthroughs there, huh?
Well, I really think that the work with Vinsariti and the part that was eventually published with Peter Clifton was quite a breakthrough. There was a little bit of controversy in the literature because it was all numerical, and at that time there were two other groups that were developing kind of analytically based approaches which conceptually were similar to ours, but they were not numerical, they were analytical. One was Lynn Gelhar at Socorro and his students, and the other one was Gidon Dagan at Tel Aviv University. And in fact, I spent a year at Tel Aviv University with Gidon. I think it was half a year. I spent a half a year with him. And at that time, our work with Peter Clifton was already kind of finished almost. And he just started looking in the same direction. So it was kind of an interesting discussion between us, is what you're doing, Shlomo, really stochastic hydrology? It's all numerics. And I say, well, what you're doing is very interesting analytical work, but how would you apply it in practice? And so it was a very interesting convergence of two approaches. I did not have much contact with Lynn Gelhar at the time, but later when I came back, that contact developed as well. So there were really three groups that I remember that were working at that time.
From a stochastic perspective.
From a stochastic perspective, but we were strictly numerical, except Larry Winter's work, which was strictly analytical.
Well, Peter Kitanidis you could also put in this class.
Peter Kitanidis was working also on a numerical.
Mm-hmm.
Yeah, but I think his emphasis at that time was on inversion primarily.
Yes.
It was inversion. This concept of stochastic, conditional stochastic modeling, which I think many practicing hydrologists to this day have difficulties with this concept, but one that is being pushed by many academic research groups, certainly ours, yours as well, I believe, to some extent, Jesus. and certainly Alberto here has been doing a lot of work in this area, is one which I believe, even though in practice it's not being used very much today, I think it will be used more and more in the future.
Which brings me to a topic that I wanted you to talk. I want to find your opinion. Mm-hmm. I would say, up to this, even inversion, you were working on techniques and methods that could be used and have been used effectively by many people, by field people, by consultants, by solutions to well hydraulics, development of codes, the inversion. These are very practical tools that anyone can use. My feeling is that since then, you've gone into more abstract things. We'll talk about this with Daniel and Alberto. But I feel, my perception is that since then a gap started growing between theoretical academic developments and practitioners' applications and interests. What do you feel about this gap?
I do not feel that there is a gap. I, in fact, feel that if you want to have powerful practical tools to deal with the very complex problems that groundwater hydrologists have to deal with, the subsurface is complex. And not only is it complex because whoever put the geology there, nature or God or whatever, made it complex, but because we have no direct access to it. And we have very limited information about that complex world that we have to deal with. Turbulence is a complex phenomenon from a physical standpoint, but you can describe the fluid and its properties quite well everywhere. You may not know what the velocity is everywhere, but the velocity in a turbulent flow system is stochastic in a true sense, in that no matter how much information you will gather about it, you will not know what the velocity is going to be at any given point the next moment. In hydrology, it's quite interesting. It's an epistemic problem in that you may not know what the velocity is at any point in the underground, but if you make a measurement of hydraulic conductivity at many points around it, you, in fact, will know much more about it than you did before you made those measurements. So with measurements, you can reduce the level of uncertainty about this very complex world that you have there. Now, in order to understand how to capture this very complex world of the underground with the tools that we have today, the measurement tools, the computational tools, the theoretical tools, you need a conceptual framework. And that conceptual framework has to have a certain level of abstraction if you want to bring it to anything useful. I think the gap may be an analogy, the difference between a numerical model and an analytical solution to the same problem. So someone who is used to applying numerical models, mud flow codes, and so on to real-world problems might look at analytical solutions as being really abstractions because they are so simplified in comparison to what you can do with a numerical model. One could raise the argument that analytical solutions actually have no room in the practical world. And I believe there are many people who think this way. And I strongly disagree, because it has been my experience that, in fact, analytical, and I gave you the example before of the ratio method and how the analytical solution suddenly made us understand the process much better than we did based on a numerical model, and gave us the ability to, in fact, simplify it by understanding that the solution doesn't depend on the hydraulic conductivity, coming back to this question of leakage through an aquitard, doesn't depend on what is the hydraulic conductivity of the aquitard, doesn't depend on what is the hydraulic the hydraulic storativity of the aquitard. It only depends on the diffusivity. In fact, it doesn't even depend on the diffusivity. It depends on the product of diffusivity with time divided by the elevation squared. So you can capture analytically in an abstract.
I would contend that you could reach that conclusion simply by doing a dimensional analysis.
You could do a dimensional analysis, but that
without having the analytical solution.
Of course, but that renders your problem abstract, because you cannot then build it directly into it. And I can give you another example where I really think that abstraction has led to actual practical results. And that is the area of scaling in which we have been working. And you didn't ask me about it. Stop me if this is not the time to talk about it. But if you remember, in the 1990s, in 1990, in fact, I published a paper in which I tried to interpret the observed, some people would say so-called, scale effect of dispersivity. My interpretation of that observed scale effect is entirely abstract. It is based on the concept that geology consists of a superposition or a hierarchy of things that happen on different scales, so structures on different scales, whether it's geological structure or I was working specifically about hydraulic conductivity or log hydraulic conductivity. So you have actually, you can think of hydraulic conductivity as having many, many scales, and you may encounter one or two or many of these scales in any given problem. The interpretation leads you to fractals. Fractals are a concept which is very useful but extremely abstract. And what I think this gave us was the basis for then coming in and bringing in real world things such as the original work assumed that fractals have all scales possible, but in reality, for example, you are limited to a certain size of an area. So there are real limits on the applicability of fractals. With Vittorio Di Federico, we developed still a very abstract theory in which we now bring in these limits formally into the story. And until I would say a year ago, one could argue that all of this is so abstract that it has absolutely no relevance to any application whatsoever until last year with Alberto and with Monica Riva, we were able to, in fact, come up with what we think may become a practical way of doing something that I bet you would agree with me, most people don't know how to do. And that is, if you have measurements of permeability obtained from packer tests, small-scale packer tests, and in the same field somewhere you have pumping tests, which give you transmissivities that cover a much larger area, you are thereby generating information about the transmissive or conductive properties of the medium on different scales, small scale, large scales, and so on. I am not aware of any way of bringing these multiple scale measurements into one coherent framework of analysis, geostatistical analysis in particular. How do you account for data measured on different scales within one unified framework? We published a paper jointly in Water Resources Research last year that actually suggests a way of doing it and shows how to potentially do this in an actual field site. It was the first field site where we have applied it. Whether it will apply elsewhere is something to be seen, but things are applied. And I want to remind you and any other skeptics about these abstract approaches and so on, that when we started developing finite element methods, for example, in the 1960s, most practitioners did not use any computational models of groundwater flow analysis. They weren't even familiar with finite differences. So practitioners were questioning the utility of numerical models, period, whether they are finite difference or finite elements. People who were using finite differences, which of course were older and better established, were questioning the utility of these complex finite element methodologies because the mathematics is more complex, the structure of the models are more complex. Geostatistics. Nobody knew anything about geostatistics for a long time. The mining engineers started using it way, way before groundwater hydrologists started using it. It took, I think, 2 decades at least until geostatistics became a practical tool. And all of this happened when not only people started learning what these tools can do, but were given tools, especially computational tools, that allowed them to do it without necessarily understanding all the details of the underlying mathematics. So the software will eventually come.
The big question is, and it is true, it takes sometimes a long time between the time that an idea is proposed, tools are developed, and it becomes
Yes.
common practice. What I'm not sure is what is the turning point when things become really practical. And I'm not sure it's just the development of tools by you. I'm not sure.
Not by me necessarily.
Exactly, that's the point. But the problem is if you are the only one who knows the abstraction, which, by the way, I'm not skeptical. I know that is the proper theoretical way of framing the problem. What I say is that I see it very far from what practitioners do.
Well,
And
I think where this gap that I think you are alluding to has become kind of obvious is in the stochastic hydrology area, where most practitioners don't use stochastic methods. And much of the work that is being done in stochastic hydrology is far removed from what a practitioner would use today. However, that is not entirely, I mean, this is the picture, this is the impression that many people have. I don't think that that impression is entirely correct. People are, for years, people have not cared about quantifying the uncertainty of parameters estimated using inverse methods. All they wanted to know is, what are the best estimates? How can I fit my model best to a given set of observed heads and get parameters out of it, transmissivities, sterativities. What is the degree of uncertainty in these estimates? Nobody cared about. With the development of tools such as PEST and concepts underlying these tools, statistical concept of actually quantifying uncertainty in a way that can be done with a computer code that everybody has access to based on data that people normally work with, now there is a tendency more and more to use PEST and related inverse methods such as yours, not only to estimate parameters, but come up with some statistical measures of how good these estimates are. So the next step then, which fewer people are concerned with today, is, so now I have estimated aquifer transmissivities and I know that they are uncertain. I know that my estimates are not exact. How would this impact my ability to predict heads in the future? Not to speak of concentrations of contaminants. How important is it for me to build in this uncertainty? We do not have reliable tools today to do this, to propagate this uncertainty through our model. We do have one tool that everybody can easily use, and that is Monte Carlo simulation. We can run our deterministic codes many, many times with different transmissivities generated statistically based on our knowledge of the error of estimation that we have obtained from the inverse model. But that is extremely time-consuming. So much of the work done in stochastic hydrology is an attempt to overcome this difficulty of having to run many Monte Carlo simulations. Stochastic hydrology is practical if you are willing to run Monte Carlo simulations. Everybody can do it. Everybody can understand it with minimal education about statistics. But how to skip over this very demanding process is not obvious, and we haven't reached that stage yet. There are many ideas floating around, many of them very abstract at this point, and many of them not so successful that they can be used by a practitioner to solve real problems. But that doesn't mean that we should stop searching. And I think that's where we stand. Many of these ideas have not indeed reached, and maybe will never reach, the ability to be applied in practice. But you always can fall back on Monte Carlo simulation.
I think that with respect to this, one of the breakthrough or one of the major points that you introduced was the concept and all the theoretical developments associated with equations which are directly satisfied by moments of the variables of interest, flow and transport, which dates back to 1993 and PhD dissertation of Shlomo,
Correct.
If I remember correctly.
Correct.
Can you tell us a few words about that, how it started and what type of possibilities you see for that?
Yes. Well, what are these moment equations that you're talking about? This is exactly one of the results of this attempt to propagate errors through our computational flow models and transport models without actually having to run Monte Carlo simulation. So what do you do when you run Monte Carlo simulation? You generate on the computer statistically many possible realizations of, say, transmissivity in an aquifer. Why many? Well, because you don't know exactly what it is, so you generate statistically many about the estimate that you got from the inverse method, because you know the estimate is not exact. And for each one, you solve the problem. You predict what the head is going to be 10 years from now, or what the concentrations are going to be in 100 years from now. So now you have, let's say you did it 1,000 times, very expensive, but let's say you did it, and now you have 1,000 predictions of head 10 years from now. What do you do with them? They're equally likely from a statistical standpoint. So what we normally do, we average them. We get a mean or an average head. You did that by running 1,000 simulations of a deterministic code. Is it possible that that mean itself satisfies its own equation that you could solve in one go? That is the question that we are asking. It turns out that yes, there are such equations. We refer to them as moment equations. Equations which are satisfied by the mean, which is called the first moment, or the variance, which is called the second moment, statistical moment of these heads. If you could solve these equations, we have formulated some such equations for flow and for transport. If you could solve these equations directly, you wouldn't need to run Monte Carlo simulations. So those are the moment equations. There's a big problem with them. They're complex. They involve integrals, not only differentials. They are not differential equations. They are integral differential equations, very difficult to solve. And they can never be solved exactly. You have to approximate them one way or another. So we are all working, different groups have been working for the last 20 years, not only to formulate these equations, but also to be able to get to these moments directly, whether through these integral differential equations or through other means. That is where most stochastic hydrology is heading. There's another very important element, and that is similar problems have arisen over the years in turbulence theory and other areas. So this whole idea of moment equations is not new. Our particular equations are different because we are solving somewhat different problems, but one of the key differences between what the stochastic hydrology of groundwater hydrologists and turbulent theory, for example, which is also stochastic because you never know what turbulent velocity is going to be anywhere, is that we can actually make measurements and build them into our equation. We can condition our stochastic predictions on measurements. And that is both very challenging and very interesting. And because we don't yet know how to do this other than through Monte Carlo simulation in a computationally efficient and convincing way for all kinds of problems, we are viewed as being abstract. And indeed, this is an abstract world at this point. I'm hoping that we will be able to develop it to a stage. And I think there are some good signs that for many problems we can do it by various newer techniques, techniques that are being offered, suggested by various groups as we go. But we are still groping in the dark, trying it this way, trying it that way, trying it that way. But the concept, I think, is a very interesting.
There are some concepts which are beautiful,
yes,
and which are unique to groundwater. For instance, as you say, as you condition, as you bring in further knowledge, the variability, the allowed variability changes, so the equations do change.
Oh yeah.
And the discrimination between variability and uncertainty, all these things are very singular to.
Let me tell you one thing that we already learned from these abstract equations. Abstract because they are mathematically really abstract. It's hard, unless you really know that, you don't even know what they mean. You see these integrals and differentials, abstract. One of the things we learned is, number one, the means do satisfy equations that we can write on paper. Compact equations that involve 2 or 3 or 4 terms instead of an infinite number of terms like they thought in turbulence would have to be written. The other thing we learned is that the deterministic equations of flow and transport that we use today, and in fact Alberto and I have published this very clearly in several papers, a concept that people have difficulty grasping still, but I think it will get ingrained in people's thought as time goes on. The deterministic equations that we are using are in fact nothing, when applied to these very heterogeneous domains, which is almost everywhere, are in fact nothing but a special form of these moment equations, these stochastic moments, simplified form of these stochastic moment equations. A key idea that comes out of this, which the equation tell you, is that the parameters that we are estimating from our deterministic models are not just properties of the aquifer. They are a mixture of properties of the aquifer and how much you know about heads and permeabilities and whatever else in the aquifer. In other words, they depend not only on what aquifer you're dealing with, but on the information, the type and amount of information you have about this aquifer. Meaning that if you run an inverse problem on a simple pumping test with a numerical code, let's say, and you get an estimate you get estimates of transmissivity distribution through an aquifer, and then you collect additional information, you measure heads over other periods of time in other wells and so on, and repeat the inverse calculation, you should not expect the transmissivities from these two inverse models to be the same. Not only because in one case it's harder to determine what they are than the other, but because intrinsically they mean different things. This one is an estimate of aquifer transmissivity based on a limited amount of information. This is a similar estimate based on a different amount and type of information, and theory says, and this is novel and very disturbing to some people, but
I find it fascinating.
But the theory says that in principle these two things are different from each other. If you had a way of continuing to sample the aquifer ad infinitum, which would of course turn it into a Swiss cheese and it would not be an aquifer anymore, but if you could do it without turning into the Swiss cheese, things would converge to the true properties of the aquifer. But that's not realistic. And so everything we estimate is a property of not only the aquifer, but also of the type and amount of information that you have. And to me, that's a very abstract concept, but a very useful one, because it tells you that you shouldn't be striving to determine in any unique way the properties of an aquifer, because it's impossible.
But it was also the concept which started the whole idea of embedding moment equations within inverse geostatistics methodologies, basically. So, yes, it was abstract, but it is leading to some practical results, yes. I would say.
Coming back to Monte Carlo simulation for just 1 second, whereas these moment equations, although they are difficult and difficult to solve and so on, they can be conditioned, they can be made, you can hang them on the measured values of permeability, transmissivities, and heads that you have. To do the same with Monte Carlo simulations is possible. You can take every Monte Carlo realization and condition it on data, but that is an exceedingly computation-intensive exercise that virtually nobody does. So again, from a standpoint of conceptually, is it able to solve can everybody solve stochastic equations in a way that's conditional on data? Yes, using Monte Carlo in principle. But until we have much more powerful computers than we have today, that is not going to be the practical way of doing it. And here we have a framework for doing it. So you have the computational aspect, but then there is also just this concept, this ability of gaining understanding about how information impacts what you're doing in hydrology, which I think is critical.
I still remember in '97 when I first came to Tucson, I was talking with Jesus also about that we were discussing together about what we could have done together during that period where I was staying here in Tucson, and it was immediately clear to me that you really didn't offer any choice. It was either moment equations or go home, something like that.
When you came?
Yes.
Well, that was because we were so immersed in working on that. Number one, Number two, I knew what talent I am getting here when you come here, and I wanted to take advantage of it.
So now it's Jesus' turn.
And I was not mistaken.
Well, there are other things that we are coming to an end of this portion of the interview, but there are other things that you've worked on and that we haven't talked about much.
Like
fractured media.
Fractured media, yes, indeed.
Fractured flow.
Fractured rocks. Yes.
Work with Jean and
Yes.
Paul and
Yes, yes. I became very much interested in fractured rocks as a student in Berkeley in a group that was essentially geological engineering, rock mechanics oriented. Other than Paul Witherspoon, who was a hydrologist, Dick Goodman and others, Thor Brecke and other people in that group were rock mechanicians, and also in the mining group at Berkeley, there was Professor Cook there, a very, very well-known expert in the mechanics of rocks, fractured rocks. And I remember distinctly being part of the audience in the PhD defense of David Snow, who developed one of the very first models of the permeability of a random fractured rock, where he threw fractures at random into the rock. He then assumed that the permeability of each individual fracture can be related to the square of its aperture. And so by generating apertures at random, with orientations at random, and so on, he came up with a numerical model, statistical model essentially, which told you what the equivalent permeability of this fractured rock mass is going to be. There was some earlier work that I became aware of done in Russia, which did the same but not in a statistical context, which I use to this day in my classes to illustrate to my class this concept of superposition of the permeabilities of individual fractures, how they impart a global fracture or an effective or equivalent permeability to a mass of fractured rock. And I was fascinated by this idea. And when we started working on our Nuclear Regulatory Commission project at Oracle, many of the early nuclear, and to this day actually, nuclear waste storage projects focus on fractured rocks, and some of them focus on crystalline fractured rocks. At that time, there was a lot of focus on crystalline fractured rocks, and so we were given money by the Nuclear Regulatory Commission to do some field work, not too far from Tucson, near Oracle, in granite, drill some boreholes into the granite, characterize the fractured rock, and then try to come up with an understanding of hydrology in this fractured rock in a detailed way, and relate our understanding of flow to an understanding of the fracture system. And I remember distinctly building my proposal to the Nuclear Regulatory Commission on this concept that we would go out, map out the fractures on outcrops in the boreholes, put them together into a geometric conceptual framework similar to David Snow's, and predict what the permeability of this fractured rock mass is going to be, and then actually run hydraulic tests to verify, validate, if you wish, this concept. And I was very enthusiastic about being able to do this. But the end result of that project was that I came to the conclusion that the concept doesn't work very well. In other words, we could not collect all this geometric information and turn it into hydraulic information. Translate the geometry that we knew quite well into permeability values with any degree of accuracy whatsoever. I was very disappointed. And at that time, I also traveled to Sweden. The Swedish, to this day, are working on the possibility of storing nuclear waste in granitic rocks at depths. And so they were looking at similar things to what we were looking, and I, in a very disappointing way, told the Geological Survey in Uppsala about our inability to use this idea of translating fractured geometry into hydraulics And they said, well, there's nothing new about it. We have already known this before because we have tried it in several places and it doesn't work. So that was kind of disappointing and a turning point for me, whereby there are questions, okay, so if I cannot translate geometric information about fractures into hydraulic information, how can I characterize flow in fractured rock? What is the permeability of fracture? How will I measure it? And then the idea came, well, you know what, maybe if you have enough fractures, this fractured rock will behave essentially as a porous medium, as a very heterogeneous porous medium. If only you do your pumping tests or whatever test you will be doing on a scale that captures many fractures rather than one at a time. And that then developed in my mind, in our mind, this, first of all, we knew that fractures are oriented in space, so we expected hydraulic conductivity of a fractured rock to be anisotropic. So we ran what was probably one of the early tomographic hydraulic tests, although we didn't interpret it in the current way of tomographic interpretations, where we would inject water under pressure between packers in one borehole, measure pressure responses as a function of time between packers in many other boreholes, and switch the injection interval. So we had these many pressure pulses propagating through a three-dimensional system of rocks. And Paul Shea, who conducted these experiments, was then faced with the task. He was a PhD student of mine. His name is the U.S. Geological Survey. Was faced with the task of extracting out of all this information an equivalent anisotropic hydraulic conductivity tensor, essentially, for the rock. And he came up with a beautiful, beautiful PhD dissertation based on that, which taught us a lot about just what is anisotropy in 3 dimensions, how you can measure it without necessarily drilling boreholes in what people think might be principal coordinates and so on. This is a rather well-known piece of work today. But one of the things that we also discovered is that this single permeability, whether isotropic or anisotropic, is not a very good approximation for the true properties of the rock because they are so heterogeneous on virtually every scale. And so then that is another reason or another thing that pushed us towards stochastic and geostatistical methods. We said, okay, well, mapping each fracture, we don't know what to do with all these details. So how about just making many packer test measurements in many boreholes on a small scale, and assuming that they come out of a porous medium, which is strongly heterogeneous, essentially using geostatistical and stochastic methods, what we refer to as the continuum approximation of fractured rocks. We know it doesn't work always. We know that, when you come to a scale where individual fractures dominate, you have to look at what happens in individual fracture. But when you have a mass of many fractures, relatively high density, we think that that's one way to approach fracture.
Except that from a fractal universal scaling perspective, you might think that you have these huge fractures everywhere.
In fact, it's interesting that you bring in fractals into the picture, because just right now as we speak, I have a paper in press in Geophysical Research Letters, where based on some of the fractal work that we have started with Vittorio Di Federico, and which I have then later developed in slightly other directions, I am coming up with an abstract relationship, statistical relationship between fracture lengths, the average aperture of a fracture, fracture density as measured by the so-called box counting method, and permeability. Now, what it gives me a general relationship between them. For example, we know that fracture lengths, there's a lot of data indicating that fracture lengths have a power law probability distribution. There's a lot of information suggesting that fracture apertures measured in the field, on average, so if you assign an average fracture average aperture to a fracture, it is a power of fracture lengths. And there's a range of measured power values between 0.5 and 2 in this case. There is a range. I said fracture lengths are power law distributed, probability distribution. The exponent of that power law, A, seems to be always between 1 and 3, and in most cases, 2. Fracture densities, clearly fractal, with a very narrow range of fractal dimensions. Permeabilities, there is, I think, a lot of indication that they may have fractal properties. Given all of this, we have developed a completely abstract formula which relates the variance of permeability or density to these parameters A of the power law distribution of lengths, and because there's a power law relationship to apertures, we can relate. So we come up with an interesting array of relationships between. Now you have to know these parameters to translate this abstract relationship into something that may apply at a given site. So you would have to, but at least it gives you what I think is a much more powerful way of relating fracture geometry to permeability than anything based on this individual discrete fracture concept that I was so fascinated by when I was listening to David Snow defend his dissertation. And it comes out from a completely fractal thing, a completely abstract thing. In fact, my paper, in which I developed the equation on the basis of which I came up with this fracture thing that I just told you, appeared in Water Resources Research as a little technical note and was heavily, heavily criticized by reviewers for whom it was just way too abstract and not useful at all and possibly incorrect. And I had a discussion in the literature, open discussion with some very strong critics of that thing. Which, by the way, was also true when I first published my 1990 fractal paper.
Oh, the universal scale.
Yeah. The concept is so abstract that anybody who looks at geology as geology, I have a layer here, I have a fault here, and so on. For them, what you see is the real world. This mathematical abstraction has absolutely no relevance to it. And yet, here I come up based on that mathematical abstraction with something which I think is exceedingly powerful, and my reviewers thought was extremely powerful.
So fortunately you had a good reviewer.
I had 2 reviewers, interestingly. One reviewer said, "This is a masterpiece, publish as is." I know they were all geophysicists, or at least people who are, well versed in geophysics. The other reviewer said, "This is a complete mathematical development. He could not find anything wrong, except at equation 13 there, Neuman makes such and such an assumption. Therefore, this paper should not be published." So I reread the paper. Did I really make this assumption? And of course, I did not make the assumption. So there was purely a question of misunderstanding. I explained this to the editor, and immediately the next day the paper was accepted for publication. So I think it's an interesting. I'm going to present it at the AGU meeting, by the way. So if you're going to be there,
You mean this new one?
This very last idea. It's very hard for me. As you were coming here, just before you came here, I was working on a PowerPoint presentation that I intend to give before the AGU meeting. I intend to give at a seminar at the University of Southern California. Don Chia-Tsang invited me there too. And I decided I'm going to talk about this thing, primarily because they have an expert in fractals, Professor Sahimi is there. So I want to see what he has to say about this. And I can tell you, I'm having a hard time putting together a PowerPoint presentation that people who are not well versed in the underlying concepts would understand and would not think that it's just absolute abstraction that has absolutely nothing to do with anything. Hard time.
There's one other aspect that we have not covered in this interview, which is your work about transport.
Yes, there's another aspect I don't know if you want to cover, and that is model uncertainty, although we talked about it a little bit, I think.
More uncertainty.
Yeah, we did talk
But
about
numerical methods.
Numerical methods in general.
Okay.
So about transport, you started working in transport when you came here to Tucson.
I really started working on transport when I got my first Nuclear Regulatory Commission project, because that was the focus. You know, what would happen to radioactive waste that's buried underground? How would it travel through the subsurface fracture blocks and so on? So all of those things came together.
And your very first works were about the introduction of the modified method of characteristics, if I remember correctly.
Yes. One of the problems that we realized from the literature and from our own experience is that standard methods, finite element, finite difference of solving the advection dispersion equation, which was the focus. You know, we did not look into chemistry or anything like this, so it was primarily advection and dispersion phenomena. Suffered from either numerical dispersion, where you get the numerical code, the numerical solution gives you much more of a spread than is observed in nature. Or if you suppress that, there's a chance that you'll get oscillatory results. So one or the other, the equation is plagued by one or the other because of its very nature. And so, you know, we were looking through the literature of ways to overcome this. Nobody knew how to overcome this. And I came upon what I think is a very obscure paper on oceanography, modeling transport through the ocean, which suggested this idea of splitting the problem into two and essentially looking at people were solving, there was a way of overcoming the problem by particle tracking, forward particle tracking, and then giving the particles random kicks. This is known as the method of characteristics in the groundwater literature. Method of characteristics is something much more broad, but in the groundwater literature, this is known as the method of characteristics. Lenny Conico at the U.S. Geological Survey was one of the people who popularized this among groundwater hydrologists. And it was used and is used to this day with success. But the modified method of characteristics, rather than tracing the movement of contaminant particles or tracer particles forward, traces them backwards from fixed nodes of a grid. And I saw this idea in this ocean-related publication, not a journal, but some obscure proceedings of some conference. And we started working on this. We called it not the modified method of characteristics, we called it the single-step reverse particle tracking method. Tried it in various ways. It had a beautiful property in that the longer was your time step of calculation, the more accurate were the results. The problem was that as you made the time step shorter, the worse the results became. We said, well, the solution is simple, use big time steps, right? The problem is that then you lose accuracy in other sense. But anyway, it was an interesting idea. We developed it, and I presented it at a Gordon conference in New Hampshire, I remember, or New Hampshire, well, anyway, it was one of these Gordon research conferences. And it was interesting that at the same research conference, there was Professor Douglas, a very well-known numerical analyst who has done one of the inventors of the method called alternating direction implicit solution of the diffusion equation. And his star student, Tom Russell and Douglas, developed this thing. And then the question, this little argument developed, well, who was the first one to develop this? The thing is that they, of course, are mathematicians, and they have done a much more sophisticated analysis of the properties of this thing and so on. And so the method has caught on, not in our form, more in their form. It is called the method of the modified method of characteristic. It is built into the very popular, as an option, into the very popular groundwater code MT3D. It does suffer from numerical dispersion because you have to interpolate. But it does have this property that the longer is the time step, the better it is, which really means that it's not converging to the true solution, because you expect the solution, as your time step becomes smaller and delta x, delta y becomes smaller, you expect the solution to improve, but here it becomes worse. So it turns out it suffers from mass balance problems. And to this day, people are trying to come up with ways of overcoming this mass balance problem. So right now, it is not a panacea, but it's a way to deal with the problem.
And parallel with numerical models, then you developed an impressive amount of work about analytical solutions of effective transport parameters.
Well, that actually, the work on effective transport parameters, or really dispersion.
Dispersion parameters, yes.
Was done, that's the work of Larry Winter that we kind of mentioned earlier, which was done in parallel with the Gelhar and Axness work, where they have also come up with stochastically derived expressions for dispersivity. With Vittorio Di Federico, we have then extended that to fractal random fields, multiscale random fields. But I think really our most recent work is based on moment equations of transport.
Yes,
that's the work with you and with Eric Morales-Cacique.
Which still suffers from some limitations, actually.
Well, the same limitations as all moment equations. We don't really know how to solve them with accuracy in an efficient and effective way. But conceptually, I think it changes the picture.
Yes.
It essentially says, coming back to one of the earlier questions, and one of you asked me, is how, I remember the question was, should I suggest that people use these dispersivities that come up from this graph of how and the answer is no, because if you look at these moment equations, there's a much better way of doing it in principle.
The concept is clear, yes.
The concept is very clear. We may not have the computational tools to do it properly at the present time. So right now we are in the abstract stage. But already here is another thing that came out of this. In recent years, because of this very complex nature of the dispersion problem, the transport problem, and the fact that transport doesn't seem to very often follow fixed analogy, which leads to the standard equation that everybody is using, various groups have come up with ideas how to model directly non-Fickian transport.
Sure.
So there is a method based on so-called fractional derivatives. There is a method called the continuous time random walk. And there are the moment equations, and there are different kinds of moment equations.
And the memory functions. My method.
They all have memory functions, right? But they are different memory functions, and every group was arguing that their approach subsumes all the other approaches. So with Daniel Tartakovsky, we have just published a paper in which we're trying to kind of put these things in perspective, showing what are the similarities and the differences between them. And it turns out, and John Cushman yesterday actually said exactly the same thing, that all of these approaches really fall out of one set of moment equations. You could take his equations, you can take our equations, they are almost the same, the only difference really being how they are derived. He derives his from statistical mechanics approaches. We start from the assumption that the fixed analogy does apply on some small scale. That's one difference. The other difference, however, is that our assumption allows us to condition our equations on measurements, whereas he cannot do that because he doesn't have measurements. It's all based on particles moving.
On the other hand, it's so much simpler, the final result.
The final result is exactly the same.
When it is not conditioned.
Well, you don't, I mean, you can take ours in the unconditional form.
You're probably talking about the mathematical form.
The mathematical form is identical. I mean, at least in terms of, you have an integral here with such and such term and so on. Exactly the same.
What are we forgetting with you?
I think we are forgetting about the impact of Yael on your research.
What do you want to hear about? Students, about Yael?
Yeah, how did you convince her to marry you? This is the most mysterious thing in your life that I cannot understand.
Jesus, if there is one thing that I never figured out, is how did my wife decide to marry me? I have no idea. But there's a much, much more important question to which I have absolutely no answer. Once she decided to marry me, how come she is still sticking to me? I have no idea.
Mysteries of life.
Mysteries of life.
Well,
there is magic to life, As far as my students are concerned, here is one of my star students interviewing me. You are not a student of mine, but we have been working together for many years, and you have your own students, so it's almost as if we were, colleagues forever.
Forever, yes.
Daniel is one of my star students. In fact, I have been extremely lucky of having a large number, truly a large number of what I would just call star students. Everybody in his own direction with their own ideas and quirks, but everyone is a friend. Every single one of them is a friend, and every one of them has made, every one of those star students, because not all of them were stars, but many, many of them were. Each one of them has made major contributions. And much of what we discussed here today, I use the word I try to use the word we wherever we could, for the simple reason that, in fact, many of these things we did together. Now, because the students were here for short periods of time, I'm kind of the focus around which everything goes, but without all of these students, without you guys, none of which would materialize in any way. Ideas would be floating in the air, but they would remain not only abstract, unrealized.
Thank you, Shlomo.
Thank you very much.
Thank you very much.